Okay. So hello everyone, my name is Philippe Jean. I'm a PhD student with Professor Wei Shi at Université Laval. I would like to start by acknowledging my co-authors, Alexandre Duhaut, Professor Sophie Larochelle, Professor Ines Mesedek, and Professor Wei Shi. We are all with the Center for Optics, Photonics, and Lasers. The title of my talk is Hybrid Integration of IQ Chalcogenide Microring Resonators on the Silicon Insulator Platform. I would also like to invite you to check out our most recent journal paper published on this topic in Optics Letters. So first, a brief outline of my talk. I will start by giving our motivation to do this process and the motivation in general to do hybrid integration. I'll then present you our method and fabrication process. I will say a few words on the deweighting of glass, and I will finish by presenting our experimental results and giving a brief summary and what we want to do next in this project. So why hybrid integration? Silicon photonics is pretty well known for its many strengths. We can think of its high density of integration, which enables compact devices, or its low-cost fabrication because it's CMOS compatible, or its vast photonics component library. But it still lacks in some fields such as nonlinear optics or laser, and this is in part due to silicon's strong multiphoton absorption, which leads to free carrier generation and absorption and dispersion. In contrast, chalcogenide is a highly nonlinear material that doesn't suffer from free carriers and also has weak to negligible multiphoton absorption. It also has the perks of being Reinhardt soluble and transparent in the mid-infrared. But chalcogenide photonics doesn't have a very well-developed photonics component library, and it's also difficult of fabrication because chalcogenide is pretty brittle. So the goal of an hybrid integration method would be to combine the strength of chalcogenide with silicon in order to overcome the drawbacks of silicon photonics while retaining the strength of the platform. So our hybrid integration method consists of embedding a chalcogenide microring inside the oxide cladding of the silicon uninsulated platform and using a silicon bus waveguide to couple light to and from the microresonator by evanescent coupling. So if we look at the process flow right here, the first 4 steps are done in foundry. So starting from a standard SOI wafer, the silicon structures are defined by UV lithography and etching. And then there's the oxide cladding deposition, which is pretty standard. And we have an additional step where micro trenches are etched inside the top cladding to define the chalcogenide waveguides. Next, at COPL, we did a short HF acid dip, and we did thin film deposition of the chalcogenide. And the final step is a thermal deweighting process. So the chips were fabricated at Advanced Micro Foundry, or AMF, in Singapore. Here we can see the fabricated chips. You can see a top view of the microtrench. Here you can see a side view with the sidewall inside where you can see some roughness remaining. And here you can see a FIB cut of the cross-section with the silicon waveguide here right next to the microtrench. So next, we deposited thin film of chalcogenide using electron beam evaporation. In the middle, you can see our evaporation chamber with the substrate holder, the electron beam source, and here you can see the chalcogenide glass inside the molybdenum crucible. Here you can see the substrate holder that was rotated at 80 RPM, and the deposition rate we use is 10 angstrom per second. So next, the last step in our process is a thermal deweighting step. And so what is thermal deweighting? It's a phenomenon that will occur when you deposit thin film on a non-wettable surface so that the film will actually lie in a metastable state, so that if you heat it up, it will induce a breakup of the material and it will tend to reorganize as droplets or small islands at equilibrium. So this is a phenomenon that has been studied a lot in polymers and in thin film and in metal thin films, but very little in glass. So there are 2 mechanisms at play in deweighting. The first one is pi-nodal decomposition. So if we consider a homogeneous thin film on a perfect substrate, the deweighting will actually start from random thickness and pressure variation inside the film, and which will create holes, which will grow and lead to random islands of different size and shape. And this is what we can see on the video here. You see everything that is yellow is glass, and you'll see the formation of holes and reorganization as islands. Yeah, and you notice that these islands or droplets are of different size and shape and of pretty much random arrangement on the substrate. So the second mechanism at play in dewetting is nucleation and growth. In this case, if you start from a pattern film or a templated substrate, you can actually control the size and shape of the resulting droplets after dewetting. And this is what we can see on this video here. Again, the glass is yellow and the small black dots are silicon pillars. And you'll see that holes will form around the silicon pillars and will grow, resulting in well-arranged droplets of relatively uniform size and shape. You can see that there are some defects, but overall, the size and shape are uniform and well-arranged. So what's really interesting for us is actually the deweighting dynamics around a microtrench. So everything starts from this sharp corner here, and as you eat the glass, the film will tend to flatten, and this will lead to a thinning of material around the edge. And at some point, this will cause the formation of a hole, and this hole will then grow through the combination of a rim retraction. So the rim will actually expand by self-diffusion away from the trench, and the glass that was on the sidewall will flow inside the microtrench, leaving a very flat and very nice strip waveguide. So the choice of chalcogenide for the study of deweighting is actually very important. In this work, we studied two different compositions. The first one was As2S3, which is the most common chalcogenide glass, and there's a lot of data available in the literature on its properties. But it has a relatively high TG of 200 degrees Celsius, which makes it a bit more difficult to study deweighting. So the second glass we used was As20S80, which is a lot less well known. So there's less data available in the literature, but its TG is much lower at 100 degrees C. So it makes it much easier to study deweighting inside this glass. And this is mainly because it has a lot of these sulfur-rich structures, which gives it a quasi-polymeric behavior. So in other words, it deweights pretty easily. So if we look at some example of fabricated optical waveguides from deweighting, if we check at the before and after picture, we can see here a relatively maybe worst case scenario of thin film deposition, where because the microtrench is pretty narrow, the deposition is not uniform inside the trench. And you see you have this bump, and you also have this remaining top layer, which will retract. If we look at the picture after deweighting, the rim is actually retracted outside of the picture, and the waveguide core is a very nice strip waveguide with a flat top. This is with As20S80, and we can look here at a similar picture with As2S3, where again the rim is retracted almost outside of the picture. And if we look at the waveguide core, it's a pretty nice strip waveguide. But here you still have a bit of, you still have a bit of curvature in the top. This indicates that the As2S3 actually deweights less easily, let's say, that As20S80. What's interesting is if we look at this picture, we can see that over a relatively large area, deweighting creates actually very uniform shapes, which is very good. So next, if we move to microresonators fabricated by deweighting, we can actually again see that the uniformity is pretty good over large area with very uniform deweighted microresonators. We can also see that we can control the deweighting by changing the temperature. But here, if you have too low temperature, you'll end up with incomplete deweighting. Whereas if you go too high, you might end up with a loss of material. So there's a trade-off here. So next, if we look at optical characterization of a microresonators with As2S3, these were deweighted at 320 degrees for 30 seconds. And the best Q factor we measure in these were 450,000, which is equivalent to about 1 dB per centimeter propagation loss in the waveguide. And the waveguide actually supported multiple mode. And we measured group indices of 2.51 and right around 3 for these modes. So next, the optical characterization of microresonators made with AS20S80. For these, we did deweighting at 240 degrees C for 2 minutes, and we saw a small improvement in Q factor with a value just over 600,000, which is about 0.7 dB per centimeter. And again, these were, the waveguides here were multimode, and we measured group indices of 2.36 and right around 2.3, which is a bit smaller than for AS2S3 as expected. So in conclusion, we demonstrated a new method to integrate chalcogenide microring resonators on the silicon annealer platform. We also demonstrated fabrication of optical waveguides and microring via the process of deweighting. And the next steps for us in this work is more in-depth characterization and optimization of these waveguide and microresonator. And we also want to use these microresonator to generate and use them as nonlinear optical source. We think with nonlinear effects such as Kerr effect or Raman effect to do lasers. Finally, I would like to acknowledge our support by Sentinel North and CERC and the CMC Microsystem for a fabrication subsidy. And I would also like to thank you for your attention.